Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back to the nanoHUB-U course, Thermal Energy at the Nanoscale. I'm Tim Fisher, and we're in the middle of week 5. Today we're going to talk about interfacial transmission, a little bit different than scattering in the sense that now we're looking at dissimilar materials in general and what happens when energy tries to flow across or between them. We're going to start with kind of going back to some of our original concepts, a chain of atoms. In this case, we're going to take the continuum approach and talk about strings that are under tension, but they have different mass densities. And so if mass density we'll call mu, and that'll come up a few times later, so just remember that. And the velocity with which a wave moves, I've just drawn some random shapes here. The velocity with which a wave moves is related to the mass density and the tension as shown in the bottom right-hand equation. So what we're interested here is a wave that's moving from left to right, and it's only in one of the strings, and then it sees this interface. So what happens is that part of the wave reflects, so it goes down this way and comes back from where it came, or goes back to where it came from. And then part of it in the right-hand string, that's a different material, will transmit. Okay, and that's the green. What we would like to do is to understand if we can mathematically derive the probability or the fraction of the wave that would go back, that would reflect, and the fraction that would go through. And so what we're going to do, there's some, this is very simple right now, but it's actually quite surprisingly powerful just to think of this string problem at first. So we will define the displacement in the left-hand string, that's the blue, as F1. And then we will say that its reflected wave will have a displacement of G. And the transmitted part of the wave will have a displacement of F. And so these are waves, and so there's a time and a position, time t, position x factor that we need to keep track of, because these are moving waves. So we can look at these. If we look at just the left string, we'll call that subscript 1. Its displacement, the transverse displacement in the string, will simply be the sum of the incoming wave, that was the F1, and the reflected wave, that was G. And then on the right-hand side, the only time it will ever move is when a wave transmits into it, because by assumption, the wave was moving from left to right from the beginning. Then there's some boundary conditions. Of course, the displacement at the interface, that's x equals 0, has to be equal for both strings. And then we'll also say that the derivative of displacement has to be equal on both sides, so that, in other words, the slope of the string at the interface, or the combined strings at the interface, will be continuous. So that's essentially just saying that there's going to be some continuity of momentum transfer across that interface. If we make those boundary conditions, we can actually solve this. Again, we haven't even invoked any sort of differential mathematics so far. But when we solve these things, we have velocities. Each string has a velocity that's specific to it. We're assuming here that the strings are under the same tension. That means the same force is being applied at the two ends, equal and opposite, to keep them at a certain tension. And we can actually solve for the displacement F2, that's the transmitted displacement, and G in terms of the incoming wave displacement F1. And when we do that, just simple algebra at this point, we find that we can solve for F2 transmitted and G in terms of F1, and then we can express them in terms of each other. So G is related to, so that the reflected amplitude or displacement is related to the transmitted amplitude or displacement, as shown here. And what we find is that if the velocity, the wave velocity in both strings are the same, wave velocities are the same, then nothing is reflected. That's as if it's just one string of the same kind, and that's what we would expect. There was nothing to create a reflected wave, and so nothing reflects. On the other hand, if the velocity in the right-hand string is 0, meaning that it has a mass density mu that goes to infinity, then everything is reflected. And that's also what we would expect. The other string becomes kind of like a wall. Now, it's great that we can relate the displacements to each other, but we're really interested in energy flow. So we've only looked at those displacements and velocities so far. We can find the rate of energy flow. We can define that as, we'll call that the symbol P. It's 1/2 times the mass density mu times the maximum displacement times the velocity. So this would give me some units of watts, for example. And so we have this factor, energy flow. We notice that it's proportional to the displacement squared. And so all other things being equal, we can say that the ratio of reflected energy at the interface, this is reflected to incident, meaning that mu is the same, because we're on the left side of the interface in this case, and V is the same. So this reflected energy coefficient, that would be P subscript G, divided by the input or incident energy, that's P subscript F1, is just the ratio of those displacements squared, which again, from our previous derivation, we can relate to velocities. And as you might expect, if the velocity, the wave velocity in medium 1 is the same as medium 2, then nothing is reflected, and so this ratio of energy flows will be 0 because nothing will be reflected. Now it's common to, instead of work with tension and mass density and even velocity, it's more common to use a concept called acoustic impedance, and that is symbolized with Z here, and it is basically the ratio of tension to velocity. And if you just do a little bit of algebra on these things in the way that we've defined them, it's also the product of mass density mu and velocity v. So then we look at, if we want to look at this this transmittance, I'm going to call it. This is again an energy-based function. That's the fraction of energy that is transmitted from medium 1 to medium 2. So that's what this subscript 1, 2 signifies. And we're going to start to see a lot of subscripts when we deal with interface problems. So it's important to keep track of them. The transmittance will just be 1 minus the reflectance that we derived on the last slide. And if you just do a little bit of simple math on this, you'll find that it can be related to these acoustic impedances. And so when we look at, in the end, the way that you'll commonly see this written is as a product of the acoustic impedances divided by the sum squared of the acoustic impedances. And of course, if the two media 1 and 2 have the same acoustic impedance, then the transmittance will be 1, because I'll have 4 times Z1 times Z2 in the numerator, and I'll have the same thing in the denominator. So this model, the basis of this model at least, is called the acoustic mismatch model. And for phonons, it was first reported and first kind of documented well by Little way back in the 1950s. Let's think a little bit more broadly about this problem. What really happens, and specifically with respect to phonons, we were solving problems in which we had a hot reservoir and a cold reservoir, and we had a device in between. But now we have an interface that's somewhere inside the device, or it may even be at the interface between a reservoir and the device. But the way I've drawn it here is that the interface exists in the middle of the device. And what we did before, we were always presuming that the device had the same number of modes throughout it. That's that concept that we talked about in week 4. But now, with this problem, we'll have actually the potential for having different numbers of modes on either side of the interface inside of the device. And just to remind you, the number of modes in the device, that's related to the number of transverse wavelengths or half wavelengths that can fit into the device. But generally speaking, it was a product of area, in quotes, because it depends on the dimensionality. In the case I've drawn here, it's a 2-dimensional problem, so that the area is W. And then the product of the average velocity in the direction of interest and the density of states in the dimensionality of the problem. So that's our number of modes, and it can change from one side to the other. You could see that, simply if the group velocity were to change, for example, you could have a change in the number of modes. And certainly there's ways to change the density of states. And so we have to be very careful about what's happening at an interface as compared to just a pure scattering event, which we talked about in the last couple of lectures. The other thing we need to make sure that we do is to conserve energy, make sure that we're not adding more carriers than can exist. And so this, we're going to revise our transport integral to account for this mode discontinuity. When we do that, what we have is we'll take the mode number and the transmittance from 1 to 2 will give us the mode number in region 1 of the device, shown on the last slide. We have these terms, right? And we take that product, multiply it by the distribution function that's feeding it from the reservoir on the left, and that's going to tell us how much of the material how much of the carrier ensemble is going to reach the other side, because that's the 1-2 signifies the transport from medium 1 to medium 2. At the same time, we're going to have to do the right to left term, and those are circled now here, and that's the number of modes in medium 2 multiplied by the transmittance from medium 2 into medium 1. That's going to tell us what goes from all the way from the far end of the right side across the device and into the left reservoir. And so there's some averaging that we'll need to do, and again, this is a fairly simple representation, and a lot of details that go into the different factors that make up the transmittances, and we'll get to some of those in this course. But what we do recognize is that the most important thing is that if I have reservoirs that are at the same temperature, that is T1 equals T2, then I know that I better get no net heat flow. The net heat flow needs to be 0 in that case. And so we have a constraint on this mode transmittance product, and we'll just say that whether we take M1 times T12 or M2 times T21, we'll call that M times script T, which is our transmission function from before. All right, so that's going to represent, either way, we will represent that as M times script T, and we could calculate it from either of these other forms. So if we apply it to the acoustic mismatch model, and I'm just going to do this in one dimension just to sort of illustrate it. For the acoustic mismatch model, what we find is that if we have just one mode, so we look at a one-dimensional problem, then for that case, if M will be one mode on both sides, M1 will equal 1 and M2 will equal 1, and what that detailed balance tells us then is that the transmittance from 1 to 2 has to equal the transmittance from 2 to 1 because they both have the same number of modes, which is 1. And therefore, my transmission function, that script t, is equal to t12 and t21. And indeed, what we found before is that for that case, for the acoustic mismatch model, again, in a one-dimensional problem, that was just the product of the acoustic impedances times 4 divided by the sum of the acoustic impedances squared. And so the acoustic impedance for the one-dimensional problem that we had studied with the strings under tension, the acoustic impedance was defined as the mass density times velocity, and that was in one dimension. But if we had a three-dimensional problem, then the acoustic mismatch, what you'll see if you look it up, you'll find that it's the mass density in three-dimensional space, rho, multiplied by the group velocity. Now, the three-dimensional issue is important, and I don't want to trivialize it. In fact, what happens with acoustic mismatch is when you have off-angled or off-normal incident, which of course most of these carriers will be when they approach an interface, they won't be coming straight onto the perpendicularly into the interface, then you have to do some geometry, and it gets a little bit complicated, but you have something like Fresnel equations to handle that. There's essentially a refraction effect that is related to, again, this density velocity product, which is the acoustic impedance, very much like what you have for the index of refraction in light. Now, often, this is a fairly complicated process, especially if you have anisotropic materials. There's a lot of different factors that can complicate the analysis. But I'll just mention here the last bullet that approximate averages are often used for this transmission, averaging over the geometric regions, three-dimensional spaces, and such. So the next type of model I want to talk about, and we'll only get a chance to talk about two, is very different. It's called the diffuse mismatch model. And in this model, what we assume, first and foremost, is that a carrier comes into an interface, and because of the physical structure of that interface, it loses its memory. It loses its memory of where it came from, meaning the direction it was going, and it loses even memory of the type or branch or polarization that it was carrying. And so this is particularly, this type of model, this diffuse mismatch model, is especially appropriate for interfaces that are very rough compared to the carrier wavelength. Again, it gets back a little bit to the problem that we talked about earlier with boundary scattering if we have a rough surface. And so what happens is with this, if you imagine now a carrier, and it could be, if we start in material 1, the carrier comes into the interface and at least has some probability that it will transmit to the other side. At the same time, you can have carriers coming from material 2, and then some of those carriers will reflect. Now, if I'm an observer in material 2 and I see this influx of carriers, I won't know whether they were transmitted or reflected because everything is getting mixed up at that interface. And therefore, the only thing we can say is that in this model is that the transmittance from material 1 to material 2, that's T12, has to equal the reflectance from material 2 to material 1, or the R21. It's really the reflectance inside of material 2. And so, if that's sort of the overriding assumption of this model, and everything else falls from that, if we just add a conservation statement, that is that whatever happens, a carrier has to be transmitted or reflected. So that means that the transmittance plus the reflectance has to equal 1 for carriers starting from one side. And that means I get at this bottom equation that the transmittance from material 1 to material 2 equals 1 minus the transmittance from material 2 to material 1. That's a really important result for this model. So again, continuing on with this diffuse mismatch model, we'll apply detailed balance. That still applies here. We still have to, in other words, regardless of what's happening with these transmission functions, when the temperatures of the two reservoirs are the same, we have to have zero heat flow. So we apply detailed balance, but now we're mixing up all of the modes, all of the branches. And so we're putting these summations onto our statement of detailed balance. And I think it's important for you to appreciate why we're doing that. It's because all these modes are being potentially mixed up together. And ultimately what we want to do is just conserve energy. What we find in this process, again, just substituting what we did on the last slide, that is that the transmittance from 2 to 1 equals 1 minus the transmittance from 1 to 2. Again, we can still have different numbers of modes on each side, and so we have to keep those factors m around. We go ahead and pull this out. If we, again, the transmission function or the transmittance is independent of the branch, that means that we can pull these T12 and T21 out of the summations, and we solve for T12. It turns out, and this is really interesting, that the transmittance, T12, is simply the fraction of modes in medium 2 relative to the total fraction of modes in media 1 and 2, in both mediums combined. And that really kind of tells you, well, it's if I have a lot of modes in this medium 2, then I'll have a preference for the phonons going into those. And if I have fewer modes in medium 2, then I'll have less transmission, and so I'll get more reflectance as a carrier goes from medium 1 to the interface. So then we can express the product of m times our transmission function. That's the script t that I'm circling now, or putting a box around, is just the number of modes in medium 1 times this ratio of modes in medium 2 to the total number of modes in both 1 and 2. If we apply then the Debye model to this, where, if you'll recall, the number of modes is proportional to the group velocity to the power minus d minus 1, or 1 divided by the velocity to the power d minus 1, where d is dimensionality, we find that we can actually express this product of m and t, transmission function, in terms of the number of modes in medium 1 and then summations of velocity, because everything else in that mode number cancels. So that's an interesting result. You'll actually see that quite a bit in the literature when they use the Debye model. You won't see this expressed in terms of the number of modes very often, but at the end of the process, you'll often see, especially for three-dimensional interfaces, you'll see 1 divided by velocity squared. So that would be appropriate for a three-dimensional problem here. All right, so we are engineers. I don't know if everyone in the audience is, but certainly I am. And we'd like to know how we actually use this information in calculations or in comparison to experiments. And so ultimately what we do is to turn our analysis into something that we can measure, and that's usually a thermal resistance, a thermal boundary resistance, sometimes a thermal conductance, which is the inverse. But a thermal boundary resistance will be the difference in temperature, delta T, between the two sides, divided by Q. That's the rate of heat flow between the two sides. And this is neglecting or not really neglecting, but assuming that there are no other impedance or resistive effects within the media themselves. And if there are, we have to subtract those out. But when we do this, all we do is say that we form this ratio. Again, our Landauer expression for the rate of heat flow, that goes in the denominator. And then what's typically done is we make the delta T very small, which it will be in real life at true interfaces. When we do that, then we turn this difference in distribution functions into a temperature derivative, and we proceed. We end up with a very simple expression for thermal boundary resistance, where the central player in it is, again, that product of the number of modes m and the transmission function script t. You'll also see it often, maybe more often, expressed normalized by area, in which case, instead of having the rate of heat flow, that would be in watts, for example, in the denominator, we have the heat flux, and that's J sub Q, the way we've been writing it. And to do that, to express it that way, all we do, because remember that the number of modes is actually the area, in quotes, multiplied by the mode density. So that mode density, if you'll recall from before, was a dimensionally dependent term. So again, this area normalized thermal boundary resistance looks very much like the regular thermal boundary resistance. The only thing we do is that we use the mode density instead of the number of modes. So how does all this look in the end? Well, I pulled a graph out of one of the seminal papers on this subject of thermal boundary resistance. It's a paper by Schwartz and Pohl. The reference is given here. And so what they did is calculate the ratio of thermal boundary resistance for diffuse mismatch model and acoustic mismatch model. They didn't really calculate it. This is more of a qualitative chart. They are expressing this ratio as a function of the material dissimilarity. So if the materials are very dissimilar, that means that that they have, let's say I have a gas and a solid, and that's the Kapitsa case here, then what this result is telling us, this notional chart is telling us, is that the diffuse mismatch model will predict a much lower thermal boundary resistance than the acoustic mismatch model. The acoustic mismatch model is the one that one would typically use. For solids, it's kind of in this, for solid-solid interfaces, those are typically moderately dissimilar, and so the ratio of diffuse mismatch and acoustic mismatch resistances will be close to 1. Again, there's a pretty big range here. And then if the materials have no dissimilarity at all, then the diffuse mismatch model will greatly overpredict the thermal resistance as compared to the acoustic mismatch model, which will essentially predict no resistance, no effective resistance, because the materials are the same. Now, I shouldn't say no effective resistance. There's a finite conductance that comes even from the acoustic mismatch model. It gets back to a conversation about the ballistic nature of the transport. So with that, I'll finish this lecture and look forward to talking to you next time.